Hello everyone, good morning. My name is Dan Lienege, and I'm a PhD candidate at the Ohio State University. It's great to be here at this year's ISNET conference. I hope you all are enjoying your time so far. Today I'll be talking about transfer learning emulation, and these are my collaborators on this project. Uh, and in my presentation, first I will introduce the method or theory behind the transfer learning emulation, and then show you a couple of interesting examples where we apply this technique to different problems. So before I talk about transfer learning, let me quickly recap what is emulation. Emulation is building computationally cheap surrogates that can interpolate and predict output of a computational expensive simulation after we train it on a sparse set of simulation data. And I'm sure a lot of you are familiar with this from yesterday's Jordan's talk. And the transfer learning emulation is about using knowledge encoded in existing trained emulators when building new emulators for similar computer simulation. The existing trained emulators, we call them the sources, and the transfer of knowledge from the source make it possible to build emulators for an expensive simulation, which we call the target, with far less training data. The transfer of knowledge from source to the target is done by assuming a linear, some form of a relationship between the two. And for this work, we assume a linear relationship as follow. The Gaussian here, ZS theta is a Gaussian process for the source. And this is basically a emulator that already exists for older simulation. Then we have the delta theta, which is a discrepancy Gaussian process, which we just add here. And it is there to learn the differences between the target and the source simulation. And then you also have this parameter rho, which is just a constant, and it scales the source emulator output. And all of these parameters, the rho and the hyperparameters in this discrepancy Gaussian process delta theta, are found by using a maximum likelihood approach using the training simulation data from the target. Now let's look at, before we move to the toy problem, let me tell you one more thing. So in this linear relationship, there's one limitation, which is that here we assume the source and the target both have the same number of or the same model parameters as their inputs. And this is a limitation in the current method, and we hope to relax this constraint in our future work. Right, let's move on to our toy problem. Here we are going to look at a spring mass oscillator system with friction. And here we are considering two spring mass oscillator systems. I call them the red and the blue. And the red oscillator, the displacement of the red oscillator with time is given by these equations. And here the red oscillator is, we assume the red oscillator to have more friction than the blue. And as you can see from this nice animation, you can see both oscillators have the same frequency, but the red gets damped pretty quickly compared to the blue. So the red has more friction than the blue. And now we are going to assume that evaluating this above mathematical expressions, which gives you the displacement of the oscillator as a function of time, is very computationally expensive. And we are also going to assume that we have emulator, a very good emulator for the red spring mass system. And we are going to take this emulator as the source. And now the task is to build a new emulator for this new simulation that we call the blue. And that is basically our target. Now let's see. Okay, so before we go and talk about the transfer learning emulation, let's look at the red emulator, which we take to be granted. Um, and here to build the red emulator, we use 100 design points in the range from 0 to 60 seconds, randomly chosen. And you can see these training points as red dots. And we also show in this plot the mean prediction of our trained GP and also the true simulation, but you cannot distinguish the two because they overlap with each other. So we have a very good emulator, and The after we train our emulator on these red data points, the hyperparameters of our Gaussian process, the length scales and the white noise variance are shown in this shown right here. Now let's move on to the transfer learning emulation. So we are trying to build an emulator for our blue simulation, and we use this knowledge transfer equation. And let me first go and describe this left side plot that you see here. So in this plot, in this color green, the dash green curve is the true simulation displacement as a function of time for our blue spring mass system. And from this simulation we take 10 randomly chosen design points. They are shown in this blue as these blue dots, and now we try to train our transfer learning emulators using these 10 training points. Basically we are going to find the parameter rho and the hyperparameters in this delta theta discrepancy gp that will fit these 10 data points. And when we do that, and when we ask the transfer learning methods to predict the mean for this time range, what we get is shown in this blue color, and the uncertainty bands are also in blue. So from here, it's clear that the transfer learning methods are very accurate, and even with 10 data points, it predicts a mean which is very closer to the green line. And when the green line when the transfer learning mean deviates from the true simulation, which is the green line, the uncertainty bands grow, and that means we have a good uncertainty quantification also that comes from this transfer learning methods. And one interesting thing to notice is here we also build a Gaussian process emulator by using just these 10 data points, and that is shown in this orange color. So if we train a Gaussian process emulator with these 10 data points, this is what we get. The mean when we ask it to predict mean, it just predicts a zero mean. So it's just a line, and then it has some uncertainty band, and it just completely miss the true simulation, and it just performs terribly. And this is a very good example where we see how good the transfer learning methods can be compared to the more traditional emulation methods. And on this right hand side plots, we keep increasing the number of training data that we get from the target. So here we have 20 design points, the 20 blue dots, and here we have 30 blue dots. And as you can see, when we keep increasing the number of training data, both of the emulation methods get better. They start to follow the true simulation, which is in the green line. And I think the Gaussian process actually uh, improves very significantly, but the transfer learning methods are also improving. And interestingly, in this last plot, we can see that even with 30 design points, the transfer learning methods still outperform the Gaussian process methods. If you look at here, the orange line is still further away from the green line, which is the true simulation output, and the uncertainty bands are still way bigger than the transfer learning uncertainty bands. So this is very promising. Now let's try to do something new, and we'll try to break transfer learning. As my good friend Pablo would say, we can learn a lot of things by trying to break things. So, and here we think that the transfer learning methods will break or will perform poorly when the source and the target are very different. So then this knowledge transfer wouldn't be very efficient, and that's what exactly we are going to do. And we are going to again look at two oscillators, the red and the blue. And now we are going to assume the red oscillator has 3 times the frequency of the blue. And as you can see from this plot, the red just moves very quickly, and both of them have the same friction, so they get dampened in a similar way, but the red just moves very quickly. So here we assume, I mean, here these two simulations are very different, I mean, as we can see. Now, again, our task is to build an emulator for the blue. Right. So, okay. So here we have the results. Again, these plots contain the true simulation in green curve as a green curve, and then the Gaussian process and the transfer learning predictions in orange and blue. And as you can see from both of these plots, where we have first we have 10 design points and then we have 30 design points. In both of these cases, the basically the transfer learning methods perform as same as a Gaussian process emulator. And in here there's you can I mean there's a little subtle difference between the two. That you can see this wiggliness that comes from the high frequency of the red oscillator, the red spring mass system, but it is negligible. And this is again very promising, because this tells us in the worst case scenario the transfer learning methods perform as good as a Gaussian process emulator, which is the next best thing that we can do. And if you take a closer look, we can see this happens because when we try to train the transfer learning emulators for these two cases, our raw value is almost close to zero. That means the effect of the red emulator is also almost negligible, and our transfer learning emulator just becomes a Gaussian process emulator that we identify with delta theta. Right. So now let's go and talk about some real world applications of these transfer learning methods. And these applications come from relativistic heavy ion collisions. So relativistic heavy ion collisions are simulated using this multi-stage dynamical approach, as shown in this nice figure. We have the initial condition stage, where we have two incoming nuclei in relativistic speeds and colliding with each other, making this hot and dense state of matter, and which we call the quark-gluon plasma. And then this highly out of equilibrium state of matter expands and cools down using some pre-equilibrium dynamics. And then as it cools down, it gets closer to some equilibrium phase. And in that, from that stage onwards, we can model the evolution of this quark-gluon plasma using a viscous hydrodynamic stage. And and when it further cools down, um, this this hot and dense matter gets converted into particles, and that is taken care by this particleization stage. And here one thing to note is that when we convert the fluid into particles, we are going to map the energy momentum tensor of the fluid cells into the momentum distribution of these hadrons. And this mapping is not unique. There are it is degenerate. So there exist multiple physics assumptions that try to model this mapping, and I have listed some of the assumptions here, different modules that we have for this particleization stage here. And we will uh, talk more about these in my next slides. Then after that we have the particles, and we have afterburner stage, where we evolve these hadrons using a hadron transport code until they are detected. And and here in this table I have listed few subset of models that are out there that we can use to model each stage of this dynamical evolution. And these different models have slightly different physics assumptions built into them. and and as you can see, by taking any combination of these models on this table, we can get a unique model that describes the relativistic heavy ion collisions. And there exist many models. Like even from this table, you can see there exist hundreds of models, and this we call the curse of model ambiguity. And one thing to note here is that although these models are different, they also share a lot of things in common. And we will use this fact later on when we build transfer learning emulations. Also, on top of this complexity, we can also consider different colliding nuclei at different energies, and it just adds on to this complexity, and it just multiplies the number of models that we have. So how do we study this quark-gluon plasma, which is made in these relativistic heavy ion collisions? uh, we have What we do is we do simulations. We have simulations, and then we compare these simulations with the experimental data. And then we try to find the parameters in our simulations that can best fit our experimental data. So to do this, we use this probabilistic framework, which we call the Bayesian parameter inference. What we are after is the posterior, which is the probability of our model parameters given the experimental data, and this is equal to the likelihood times the prior, the divided by some normalization, and this is just simply the base rule. The likelihood is the probability of observing the experimental data if our model parameter value is theta, and the prior is a prior belief that we have about the model parameter values theta. And if we take a closer look at the likelihood, it usually takes this normal form, and it has both the experimental data and the simulation output for model parameter value theta. And this is analytically intractable. And if we want to get a posterior, a robust posterior, and if we want to explore the posterior, and if we want to find out the shape of the posterior, we need to use a sampling technique like Markov chain Monte Carlo, to take samples of this posterior, and to do that we have to evaluate this likelihood millions of times for different parameter values of theta. And again, this becomes computationally impossible because our simulation is very computationally expensive. So as a workaround to that problem, we build emulators. So as I said before, emulators are computationally cheap surrogates that can predict and interpolate simulation outputs without actually running the simulation after we train it on a sparse set of simulation data. And now the most computationally expensive part is getting the training data for these emulators. And as I mentioned in the previous slide, if we want to construct and consider all these multiple models that exist for relativistic heavy ion collisions, we need to build emulators for each of these different models, and it again becomes too computationally expensive. And that is why we think this new method that we propose will be very useful. And in this new method that we propose, the transfer learning techniques use general trends in existing trained emulator models when building emulators for new models. Right. So now let's go and talk about one of the applications of transfer learning methods. And all the examples that I show from here onwards use Jetscape sim simulation data from this very recent 2021 publication on getting Bayesian parameter estimate for QCD matter. And here, as the first example, we will try to build emulators for different collision systems at different energies. So here, our source emulator, our source emulator is going to be late collisions at 2.76 TeV. So these are the simulations that we are going to take as granted. These are the older simulations, and based on them, we will try to build new emulators for gold collisions. So different nuclei and colliding at a different energy of 200 GeV. So if we do that, this is what we get. So in these plots on the right hand side, these 6 plots show 6 emulators. So we build emulators for each of these different observables, and we build emulators in 2 methods. We build the transfer learning emulators and also Gaussian process emulators, and we build these emulators while increasing the number of training data points that we get from the target. And at each step, we are going to calculate emulator accuracy using a test data set that we get from the target. And we are basically calculating the mean square error of our emulators. And that's what you see in these plots. So let me show you this plot where I have averaged this emulator accuracy over all of these observables and put it here. And as you can see clearly, the transfer learning methods, which is in this blue color, have a smaller mean squared error. So the emulators are very accurate, even with a smaller number of sample size. And it reaches quickly to the desired accuracy that we want, while the Gaussian process emulators take much more samples to reach the same accuracy. And this shows how effective the transfer learning methods can be. Now let's go to a different application of transfer learning methods. Here we are considering 2 different models for relativistic heavy ion collision. So as a source, we will take these combination of modules, uh, and the simulation with this combination of modules as our source, and our target, the new simulation that we want to build emulators for is going to have the same modules except for particularization. Instead of the grad module, we'll be using this Pratt-Torrey-Bernhard module. And so for this new target, this is what we get. Again, we are going to build 10 emulators for these 10 different observables, and we are going to use uh, these two different emulation methods, the Gaussian process and the transfer learning. And we are going to keep increasing the number of training points that we get from the target and compare the emulation accuracy scores between the two. And on this left side plot, I show the averaged emulation accuracy over these 10 emulators. And again, what we see is the transfer learning methods quickly converge to the desired accuracy, while it takes a lot more samples from the training, the target, uh, to while it takes a lot more samples for the Gaussian process to convert converge to the same level of accuracy. Right, this brings me to the last example that I have here. Again, we are going to look at two different models that we have for relativistic Kvyat collision. One with the grad viscous correction as the particleization, and the other one with the Chapman N-square viscous corrections as the particleization. And again, we are going to build emulators for these 10 different observables. And we are going to do it in two methods, the transfer learning emulation and the Gaussian process emulation. And in this plot, again, I show the averaged mean square error accuracy for the two emulation methods. And surprisingly, you can see that here, even with a sample size of like 25, we converge to the desired accuracy that we want, while it takes a lot more samples for the Gaussian process to converge to the same level of accuracy. And this is quite surprising, and this shows how powerful the transfer learning methods can be in some cases. So in summary, I first talked about the studying theoretical uncertainties in relativistic heavy ion collisions require many simulations. And then we talked that the biggest computational cost is associated with getting full model data for training Gaussian process emulators. And in this work, we have proposed a new sustainable, cheap and accurate alternative to lower this computational barrier. And from this plot where we have the computational saving, you can see the transfer learning methods sometimes, like for some simulations, saves computational time by a factor of almost like 10. And it's great, so we can use it when we want to build emulators for new computer simulations. And the transfer learning based Gaussian process emulators achieve this by using the general trends from trained emulators for existing models when we are building emulators for newer models. And before I finish, I also want to let you know that all the code that I used for this work is available in GitHub if you follow this link. And also I use this Manim library to generate these animations, and it's great. If you should check it out if you have some time. And also I used the Emu kit to get the tools that I need to implement these transfer learning methods. Thank you, and I'll take questions now.